Okay, so we're on to part B of homework 2. This time we're doing heat diffusion equations. So first we're going to derive that time-dependent heat diffusion equation for a uniform linear bar. Then we'll kind of do a backward differencing where we express that in terms of, um, I guess, iterations or discretizations, I should say. Then we'll go ahead and graph that in Python with our collab as usual, and then do a Neumann stability analysis with that R term, which will be explained here in quite a bit. So let's just get started. So we have a uniform bar. Forgive my artistic abilities, but I'll try the best I can. Something like this. Okay. And then we have, we're eventually going to be discretizing this, but we'll focus on like a infinitely small slice. We'll call that our dx. And I think eventually we'll write it something like delta x. So just know that those things are the exact same thing. So with this uniform linear bar, heat is flowing from the x direction. I'm going to define the positive direction as from left to right. And then we also have a cross-sectional area A. This bar also has a density, some specific heat, and I believe that's all we need for our energy balance, which is what we're going to be doing. Eventually, we have one side that is set to 40 degrees, the other is set to 80 degrees Celsius, and then we're going to model those changes in temperature over time as well as position. So that's what we'll be deriving. So energy balance, as usual, focusing on temperature, sensible heat, not latent heat. Obviously, no change of matter changes, I guess. So yeah, let's just get started. We remember our expression for the energy equation or energy balance was Q was equal to the mass times the specific heat times the change in temperature. And we know that the temperature, we always use a reference temperature of 0. So that allowed us just to say that our temperature was just T. So with our bar, what do we have? Well, we have a density. We're trying to break down this mass since we don't have a given mass. So we have density, and usually we multiply that by volume as we did in previous videos. But as you can tell, I'm going to go ahead and say we don't have volume. So another way we can define that volume, well, we have a cross-sectional slice A and a infinitely small width of x, delta x, dx, however you want to call it. So breaking that volume even further, we have our cross-sectional area A times our width dx. So those will be the terms that we're going to be using along with our, oh my goodness, specific heat and our temperature. So obviously we're interested in the change of time. So trying to turn this into a differential, we have our density times our area and width dx, our specific heat C, and then we're interested in differential once again, temperature over time. So breaking down units, as we know before, this will eventually break down into watts or joules per second. Again, let's just do our usual unit breakdown. So density usually is in kilograms per meter cubed. Area, that's in meters, a meter squared, excuse me. dx is obviously, or I'm sorry, this will eventually become volume. So volume is, well, yes, meters cubed. So meters squared times meters. I don't know why I changed colors there. Meters, specific heat. So that is joules per kilogram Kelvin. And obviously our differential temperature over time is Kelvin over time. And you'll see that all the units here can cancel out. Kilogram, kilogram, meters cubed, joules, I'm sorry, not joules, Kelvin. And now we have joules over time, which as we know is simply watts. So now we're interested in what is the heat flow, since that's what's obviously dictating this energy balance here. So again, we define that the positive direction is defined from left to right for heat flow. So breaking down this very small slice block here, I guess Lego brick, we can do something like cube if I know how to draw one, something like that. Actually, I don't really need to make it a cube. It can just be kind of a square here. So I'll do a square. Well, it's still a cube. But something like, so this is our position. We have our position at x and our position at dx, or change of x. And again, this little change here, we're going to denote that as the dx, or I'm sorry, this portion should be, if that is dx, x plus dx. So we're adding on a portion, we don't know, call it whatever you want, some very small addition, some position change, that is dx. So we have our heat flow, again, positive coming in, q of x, and our heat flow coming out, q x plus dx. And you're probably wondering why I drew the heat flow going out. Well, remember that I defined our global scale of our position, our direction of heat flow from left to right. So obviously our q here has to go to the right if we want to denote it as positive. So that direction will be important as we're deriving this energy balance here. So I'm going to go ahead and move that to the side. Well, actually, just to kind of visualize, well, heat is going into the block. Q of x is going in, so that's going to be positive. So I don't know if I should, hopefully we're okay with the units here, so I'll go ahead and erase that. And kind of move on to the right-hand side of our energy balance here. Just make sure we're recording. Move this down a bit. And yeah, so the right-hand side, we have Q of x, as I said, is positive, so flowing in, and minus, because we're interested in the flow to the right, but we want it to be inside the box, so that is right to left. That is opposite the positive direction, which is why we're subtracting that amount. So it becomes qx plus dx. Again, subtracting merely because of the direction we defined. As technically, the directions don't really matter as long as you're consistent and making sure you know what directions those heat flows are coming in and out. So breaking this down, well, the heat flow for this object is defined by Fourier's law of conductivity. If you remember, we have q of x. I guess we could just write it, well, q of x is probably better here. We have q of x, it was negative k, our thermal conductivity, times area, times our temperature gradient, which with respect to position, which is just a differential dt over dx, change in temperature over change in position. You might have seen it written like this as well, with the upside down triangle representing gradient. So you're probably wondering about the sign here. That might mess things up. Well, remember our temperature, just a little simple temperature profile here. Our temperature with respect to x, we'll have some temperature increasing as we increase with position. Well, you can tell just easily looking at this graph, well, the slope is positive. That means our differential here is positive. And what you'll need to consider also what direction temperature flows in from. Obviously, it flows from high to low. So we're actually moving in the opposite direction, which is why we need to negate the slope, since the slope, naturally, given the graph, is positive. So that's just a little quick overview of Fourier's law. We also have our qx plus dx term that we should expand a bit here. Well, qx plus dx, that is just simply, let's go, same color, kind of, qx plus dx. Well, what is that? It's our original qx plus a change. So again, this is a sort of Taylor series expansion, if you remember from calc, I think it's calc 1 or calc 2. But basically, we're adding the slope of dqx with respect to x. Again, that is just a change in slope for x. And what is our slope multiplied by? Well, that's just our distance. We traveled a distance of dx. And I should mention that these derivatives are partial derivatives, such as this. I guess I should write it in more of the normal, signage or terms you would normally see it as, but kind of force of habit to, I'm sorry, that's not the right one, to write it as a d, but it is technically a partial derivative. Because again, we're taking partial derivatives of temperature with respect to position and time. So that's why they're partial. So yeah, Taylor series, if you remember it, when something like our function, expanding that function for a given interval. Again, we use Taylor series to approximate functions with finite differences. So we have f of x evaluated at some point. Remember, they were usually centered around a point that we were given, and then we evaluate it around that point so we know what intervals to use that were accurate for our polynomial functions that we derived. So usually when something like the first derivative of that point, and then the difference, so x minus c, and then that was just 0 factorial. Then you go 1 factorial, 2 factorial, and so on. I think the next one was something like double prime c x minus c squared, and then 2 factorial. So again, Taylor series, nothing out of the ordinary here. So yeah, that's what that is, just as a little tiny little detail for Taylor series of our qx plus dx. And now what you'll kind of see as we substitute our terms here for the right-hand side, well, we have qx remains as usual, minus now qx plus dx. We're just adding in our qx here. So minus qx plus derivative q dx. And it might be overkill to put a qx there, but you know what? We're just going to keep it as is. And obviously the dx, don't forget our width, or that difference that we're multiplying our slope by. So what is this? Well, you can see that our qx's here cancel out the heat flow coming in from the left-hand side. And now we have to evaluate a derivative here. We're going to evaluate our Fourier's law again for this term. So that will simply just be, it'll be a negative, but I'll keep the negative again, just so you can see. So a negative right here from our original sign, and then a negative from our Fourier's law. So the negative inside times k, our thermal conductivity, times A, our area. And then now we're taking the derivative of this term, so it'll be a second derivative. And since this is the only one of x, you're going to be doing, again, a second derivative. I don't know why I repeated myself. So it'll just be d squared t over dx squared. And don't forget our dx term, bringing that down. So nothing too bad. Again, just taking derivative, bringing down the constants, and kind of upgrading our derivative since we're taking it a derivative twice. So nothing too crazy there. And then we have our left-hand side as usual. I'll go ahead and rewrite this right side. So it will be thermal conductivity A, d squared t, I'm not sorry, d squared, but second derivative of temperature with respect to position, and dx. And break down the left-hand side, we have our density, area, dx width, our specific heat, and our differential temperature with respect to time. That equals sign here. And now you're kind of seeing our differential with respect to time and position here. We're going to be isolating those terms, so we'll move around our constants here. You can kind of see here that our areas cancel out, our dx's, our widths of our infinitely small slices cancel out, and now we're left with density, specific heat, and k, our thermal conductivity. And our final expression for this heat diffusivity will be the temperature with respect to time is equal to k, our thermal conductivity, over density times specific heat. And again, our differential second derivative of temperature with respect to position. Now this term here is pretty important. Kind of see the unit breakdown and kind of relations to previous classes you might have taken in chemical engineering, like mass transport. So go ahead and breaking this down. Almost universally, this is denoted by a term alpha, which is known as the thermal diffusivity. So kind of the whole problem, what we were doing is pretty much this. It's our thermal conductivity over density times specific heat. So I guess what's important to remember, the difference between thermal conductivity, which is K, and thermal diffusivity, alpha. Well, for a given object, let's compare two objects of the same material, so same thermal diffusivity, but maybe they're made different dimensions or different ways such that their densities and their specific heats are different. Well, let's go and say we have two bars. One bar has a very high density, a very high a very high density and very high heat capacity, and we stick one end of this bar to something that's heating it up to 1,000 Kelvin, very hot, and we're gonna say how long does it take until this thing burns me and we scream. Well, obviously, if it has a high density and a high heat capacity, those terms on the denominator are going up, so that thermal diffusivity is going to go down. And that kind of makes sense just thinking about it mathematically, but also physically. If there is a high density and a high specific heat capacity, it's just going to take more energy and more time for that heat from one end to transfer to the other. So that's kind of the difference between thermal diffusivity and, oh, did I write diffusivity twice? That's awkward. It should be conductivity at the top. So a little mistake there. Excuse me. So yeah, that's the difference. Even if things have the same thermal conductivity, again, it depends on the density and the specific heat for that thermal diffusivity. And kind of looking at the unit breakdown here, well, actually, I don't think we went and for the units for K, so let's go ahead and do that. Well, K, kind of ignoring the signs here. So Q of X, we know that's Fourier's law, heat flux, and that is just simply watts, so joules per second, is equal to K. Well, that's what we're solving for. Area, meters squared, and then temperature, well, that's just Kelvin. And then with respect to position, that differential, so K over meters. Breaking down the units here, well, it's a little awkward since we have two Ks, so I'll kind of denote our K here. So isolating for our K thermal conductivity, we have joules per second divided by meters squared times meters over Kelvin. Well, you'll see that this just breaks down into joules per second, meters on the bottom, and Kelvin on the bottom, which is, again, watts per meter per Kelvin. So that's our K. So plugging that into here, checking our units, we have watts per meter Kelvin. Density, as we know, kilogram per meter cube. Specific heat, joules per kilogram Kelvin. And I'll go ahead and turn our watts here into joules per second as well. Finding the units cancel, joules and joules, kilogram, kilogram, Kelvin, Kelvin, and you're left with 1 meter times second over meter cubed, which simplifies just to meter cube, meter second, and meter squared over second. So kind of realize these units if you remember from previous mass transport classes. This equation here, I'll go ahead and rewrite it. So we had differential with respect to temperature. I'm sorry, our change in temperature with respect to time is equal to alpha, our thermal diffusivity, and then second derivative of temperature with respect to position. Well, this is analogous to our concentration profile that we observed in mass transport, which is practically identical with D, our fixed law diffusivity, diffusion coefficient, excuse me. And again, second derivative with respect to position. And also we've seen tau, our shear stress, is equal to mu, our absolute viscosity or dynamic viscosity, times our perpendicular velocity. So velocity in the x direction with respect to y. And if you remember this mu, dynamic viscosity, we relate that to, I believe it's pronounced ni. Not too sure on that one, but our symbol for kinematic viscosity, which was simply dynamic viscosity over our density. Breaking down units here, and I should say all these units are for these coefficients highlighted here, do break down to the same exact meter squared per second, and I'll show that right here. So mu, our absolute viscosity, what is that? Pascal seconds. Kilogram, which is, or I'm sorry, density, which is kilogram per meter cubed. I'll go ahead and just leave the bottom the same. So pascals is Newton per meter squared times seconds breaking down a Newton, that is a kilogram meter per second squared. And remember, we still have seconds over meter squared. And we have kilogram meter cubed on the bottom. So checking out our units here, what do we have? Seconds on the bottom, still at the top, meters on the bottom, and then our, I guess our actual bottom, our denominator here, meters cubed and kilogram. Kilogram cancels here, and we shouldn't have that. So then you'll see what we end up getting is the same exact thing that we got before. Again, meters squared per second. So concept doesn't change. Honestly, it stays the same. But yeah, that's a kind of a little relation from mass transport. You remember those? So what we're focused on is this equation here. So I believe that is the first part. Derive the time-dependent heat diffusion equation, and for constant thermal diffusivity, what we said was alpha. And now we're going to express this with some backward differencing. All that means is that we're going to be discretizing our time and position in a way that we can actually code this out. And this will also help us with our stability analysis later on. So kind of breaking this down, I'll go ahead and rewrite this just so we have more room. But this was change in temperature with respect to time is equal to alpha, our thermal diffusivity, and then second derivative temperature with respect to position. So discretizing this, pretty easy. We're just taking a finite difference. I believe we said we're backward differencing, so we're going to be looking at the previous time values to kind of relate our differentials here. So time, temperature with respect to time, what is that? Well, we have some, I guess I should say our next time, so Tn plus 1 at some position j is subtracted from our previous time, or I guess you could say our current time at the same position, and this is over our time discretization delta t, and this must be equal to alpha, thermal diffusivity. And let's go ahead and kind of go back to our first derivative so we can kind of see where this is going. So second derivative, well, let's start with the first one. Temperature with respect to position evaluated at some position j. Well, that's pretty similar to what we did over here with our time. You want our, well, we'll be using our current time, or I guess technically previous time of n, but our j is j plus 1 since we're interested in the next direction, or I'm sorry, not the next direction, the position adjacent to it, minus our current position at the same time over our change in x. So that is just our time step. Just to kind of visualize this a little bit better, I know I was struggling with this at first. So we have our blocks. If I can draw them. Oh boy. Let me take a second here. I'll just go ahead and draw 3. Something like that. Okay. So again, we had our position j. Let's just go identify our delta x here. So delta x, so that's our change in position. And then we identified j. So I guess we'll call this middle point j. This will be j plus 1. Maybe it might be better to do these sides. So we'll do j. This is j plus 1. Oh man. J plus 1. And then this is j plus 2. Or I'm sorry, j minus 1. J minus 1. So what we just did is these two blocks next to each other. So the difference between these two, I mean, technically we could have done the center, but it makes sense either way since we're doing the forward and the backward. So we're interested in this flow and then the other flow for the previous block, which is this one. So again, I guess I'll bring these down. Sorry for the bad visual expression here. So j plus 1, j minus 1. Again, we're interested in the one from j to j plus 1 to the right, and j minus 1 to j from the left. So both of them are moving in the positive direction here. So I have identified this first derivative as in terms of j. So that's what we said this component was for j. And then the next component will be from j minus 1. And that is simply the same exact thing, but we're plugging in j minus 1 for j. So j minus 1 here, what would that be? T to the n, our current time, j plus 1, we're plugging in j minus 1. So that's just j. And then for j, we're plugging in j minus 1. That's j minus 1 over x. So now for the second derivative, well, a second derivative is just the change between the two derivatives. So again, just a rate expressing our derivative as a finite sum that's differencing, or I guess a function as a finite difference is what I should say. So I guess I'll go ahead and rewrite it. So second derivative with respect to position is our first derivative with respect to position evaluated at j minus our second derivative, or I guess first derivative, if you want to say it like that, at j minus 1 over x. Rewriting all of this, well, we had tj plus 1, if you recall, right here. Again, we wrote these terms already. J minus 1, j minus 1. So I'm just rewriting that just for some clarity. So again, these are all at the current or previous time, however you want to say, j, and we are, that's over delta x, our change, and this is subtracted, so tj n minus tj minus 1 n x over delta x. So you'll see that we'll combine these delta x's down to one term. We'll go ahead and square that, factor that out. And then combining terms here, what do we have? tjn plus 1. So bring that out. I'm sorry, tn to the j plus 1. And then recall that we have two of these identical terms. So we'll just simply subtract 2. So minus 2 tjn, and then know that this is a plus from the two negatives. So that is plus tj minus 1 n. So that's our second derivative. So putting all of this together, we have this component, we have our alpha, and then we have our left-hand side for time dependence of our temperature profile. So combining all of that together, this is, go ahead and rewrite it again. For the same position, we have the future time minus the current time at the same position for our time discretization, alpha over, I'll go ahead and separate it for now, 1 over our delta x squared. So our position, our spatial different discretization, and then our temperature term, or I'm sorry, our second derivative term, which we again change with respect to position. So the j plus 1 to that same time minus 2 of the j of the current position at the same time plus our temperature of the previous position at the same time. So kind of moving all the terms here together, I'm going to go ahead and move these two terms to the right. And what that gives us is our future term for the same position. So our temperature in the next time period at the same position j is equal to tjn, our current temperature at the current position. And I'm actually also going to combine these terms into a term for r. So r is just going to be alpha times our time over our position. So that's going to be a pretty important term later on. It kind of dictates how well, or I guess whether or not the function will oscillate. And that's just a purely mathematical expression that you'll see. Even after I plug in this expression, this r term is what's going to dictate whether or not our function goes kabloom. So very important here. I guess kind of breaking it down a little bit. Well, it's our thermal conductivity. That's a constant. So in the end, what we're changing is these time steps that you'll have to choose. And eventually we'll discover that R is limited, again, by some number. I believe it's 0.5 in the instructions for our example here. So basically what this means is that we'll have to choose a certain ratio of time steps and our position. So what this means, say we have a bar, maybe we want to cut that bar into very fine slices of even smaller of what our current x is now. And keep in mind this x term, our dx, delta x, however you want to call it, those infinitely small slices are very small. So decreasing that term even more and making sure that's squared, well, that would basically mean that we're multiplying 100. So it's, I'm sorry, it should be 10 times our 1 over x squared, something like this. And this must be proportional if we want to stay under our 0.5 golden number that will eventually derive and see why it's that golden number. It will eventually mean that we have to, if we want to increase our time steps by, I'm sorry, it should be this. Something like that. So if we want to increase the number of time steps on the bottom, again, it's on the denominator. So if we increase our time steps, more slices, a more fine resolution, we'll have to decrease our time by about 100 times that amount. So you're basically losing some, I guess, resolution in the other dimension, I guess. So kind of hard to find that special ratio when you're governed by a 0.5, I guess, limit here. So we'll go into that in more detail, but again, that's what R stands for. I don't know why I put a multiply sign here. So we just added this purple term here to the other side. Oh, no, I guess it's pink. So that's why it's a plus, and then we have our same exact I guess, list of variables that we had before. So this is what we're going to be using to plug in to our function in Python that we will graph. And let me just check here that we are finished with part 1 and part 2. So yes, we did our time-dependent heat diffusion equation. So that was right here, time dependence. And now, moving on, we have our differencing that we did. So again, expressing our discretizations with time and position right here. All right, so I guess let's just go ahead and code this out. I guess what makes more sense is if I do a sort of split screen here, something like that. Here. You know what? I think we get the point. I'll go ahead and just do it all here. Hopefully you remember the numbers. I have it right here on my iPad, so good for me, I guess. All right, so this is, what are we gonna call this? I guess thermal diffusivity. Right. Go ahead and import our libraries here. Import numpy as np. Also subplots from plotly. So from plotly dot subplots, I can spell import make subplots. And actually what I'm also going to do, since I'm a bit zoomed in here, I'll kind of do our np set print options. One for consistency with our class example. So we had position options. So position was, I believe, equal to 1. And the other one, I think it was line width. So just so we can see our list of temperatures, we're going to make an array of temperatures. So I kind of want to see that all on one line. So line width, and this changes the number of characters per line until basically a next line indent. I think mine was like 86. Let's just do 100. Enter, and yeah. So basically, I kind of already put the functions, or I guess operations we'll be using. I guess this is separate. I didn't really use it, but more of a reminder for me, honestly. So I'll get rid of that. So arange, np arange, we're going to be using this for creating the integer. I believe this is a list. I'm sorry, interval. So we'll be giving. We have our temperature, which has a. We'll be doing a t dot size to return the elements. I guess it's right here. So it returns the number of elements, basically just an integer number. So we'll be doing that based off our temperature array. And then we'll be plugging that into our numpy arange so that it creates, I guess, no, our interval, or I'm sorry, our array for our given x axis, basically. This, we want to match our x axis with our given temperature array. And then we'll be using the range function here for our loop. I believe I used this before already, but again, it has start, stop, and step parameters. We'll just be using the stop parameter so we can control our for loop. How many iterations it does, depending on if we need more or not. So I guess I forgot to put np full in there, but so np full is going to be generating a full array, as the name suggests. So I believe, what does this say? We have 20 sections of our bar initially at 50C. So we want a shape of an array. So the first parameter of 20 sections, and then filled with 50 Celsius, making sure that we have a floating point here. And if we go ahead and shift enter to display our temperature, we should have 50 all across. So actually, I think it's, I guess I'm kind of covering it. So maybe, I think default is 75. I'm not actually not sure, but as long as you can see it, I kind of want these to balance out. So maybe decreasing it would, yeah, there we go. So yeah, just more for me, the OCD, something like that. Okay. Oh, that's really zoomed in on my, okay. Next, we're going to be changing the ends of these arrays. So remember, indexing, again, from previous videos, it starts at 0, and then we can get this last element at -1. And I believe we want 40 Celsius on one side and 80 Celsius on the other side. So the left side will do indexing at 0. So this must be equal to 40 degrees C. And then our list or array for our temperature from the last element, we say it's -1, and this must be equal to 80. I'll go ahead and view our list. So yes, make sure we changed our temperatures there. Hopefully that you can see that pretty well. What's next? I think that's all we need. Yeah, let's just go ahead and plot this up. So fig1 is equal to make subplots, remembering our parentheses, and go ahead and graph our, I guess, initial values before we start iterating. So here's where I was talking about the numpy arange. So this is going to be the size again. Size captures the number of elements in our temperature array. np arange, so this is a number that will return, and then np arange formats basically a list or an array of integers of that number. So I guess it makes more sense if I kind of put it on display here. So I'll turn it into a list. np arange, I don't know, 5. So I'll print it as a list from 0 to 4. And then this t dot size, well, if I just do it down here, we'll know that it returns 20, since that's how many discretizations we made, dividing our bar into 20 sections. So again, this is just a number. If I put 20 here, it should be the exact same thing as if I put t dot size. So yeah, 0 to 19. And that should be taken care of. That also plots our y, which is just our t. our temperatures, and then making sure we're in lines. Let's go ahead and check that. Not defined. Yep, big one. And I think it should just show up. Awesome. I'm gonna go ahead and make that dark. So since it's kind of late, what was it? Templates to politely dark. Okay. So there we go. That's our that is huge. Kind of covering it here. I'll just keep it and kind of zoom out later. That is just gonna keep going. Okay. We'll worry about that later. So what's next here? You know what, I'll just do it now. Let's go width is equal to like 600. Height is equal to 400. That's better. Okay. Next, graphing this up, we'll need an iteration. So for every iteration, we're going to be changing our t. Let's do something like this up top so you can kind of visualize. So we have 20 in our, I guess, array here. And our equation, I guess this would be a good time to split screen if I can. Something like this. And that. There's one note. That. And that. Go down right here. So this is the equation we'll be using. We're literally going to just copy paste this variable by variable, I guess. So yeah, so for I, we're going to be iterating, so in a for loop. So for I in some range, remember that range is just an interval, evenly, excuse me, evenly spaced points with a stopping point as we dictate in one of the parameters here. So stop, I don't know, like 100, and then that's our for loop. So we're going to be iterating, excuse me, our for loop 100 times. And we're going to be changing our temperatures accordingly each time. So what this means is that for our temperature list here, we're going to be applying this equation. Oh, I can't see my cursor, but we're going to be applying the equation on the left. Let's take a sip. My voice is getting hoarse here, but we're going to be applying the equation on the left for that iteration of 100 times. Excuse me. So what that means is we're interested in the change of these values. So that will be what we're updating essentially, since we're saying that the ends of the bar remain the same temperature. So how do we want to code this? So yeah, our array of in the middle here, these sections set at 50, we want to capture those and update those. So this is 0, 1, all the way to the end, and then up to -1. So 1 to -1. 1 to -1. And if I do just that, you'd be able to see 1 to -1 that we are indeed capturing those constant values at 50 degrees Celsius. So again, this updated term is what we'll describe as the TJ at the same position at the next period of time. So again, at the previous period of time, we are essentially using the same position. So it will be updating the same position plus R, that is equals plus R. So I guess I should also define my R here. Here are some, I don't remember what the exact numbers were, but I'll go 0.5 for now. As long as we're under or a little over that 0.5, we should be good. So it's plus R times, so this is our next position. So we have to think about this carefully, returning back to our original array. So we have this position. We want to capture the temperature at the next position over at the same time. So next position over would be here, and next position over would be here. So again, we're shifting over. So we'll be starting at this term to this term. Again, the reason for that, the first term, we're looking at the next term over, and all the terms in between also shift over. And essentially the last term we shift over, and it also captures the last element. So at the end, what are we capturing? Well, it's 0, 1 to 2. So starting at 2 and then all the way to the end. If you remember, we can leave at the very end just an open semicolon, since it just assumes that you're going all the way to the very end. So what did I say? 0, 1, 2, I think. 0, 1, 2. So this highlighted portion, 0, 1, 2. So 2 to the very end. And that was for the next position. Then we subtract by the same position. Remember, these two are the exact same. So I subtract by the exact same amount that we're updating at the current position, or at the same position as before. And remember to multiply by 2. What else? And then this last term here on the right, the tn j minus 1. So that will be, instead of j plus 1, which is the next position over, we want the previous position. So that'll be the opposite of the first term that we had. So instead of going to the next position from our updated, so this is next position over 1. We want the previous position from the original position. So we're going over to left. So I'll be starting this, the first at 0 and the last at -2. So it'll be these highlighted portions. So just some indexing from the very beginning all the way to the end at -2. Again, -2 because we omit this, we stop at the -2nd term. Essentially this. Cool. Hopefully this works. Hopefully I'm not forgetting anything here. I think not. Oh yeah, I need to add scatter. So we want to plot this up every single time. I'm again just copy pasting, since we know our temperature at that for those indices will be changing. And then outside the loop, I'll tell it to display the figure. Oh boy. Oh yeah, brackets. That's bad. Remember, arrays, indexing, you need, oh, there's no, you need brackets. There we go. Work. Wow. Okay. So it looks like we reached the steady state with a straight slope pretty fast. We didn't actually need to go to 100. But I mean, that's pretty straight. I guess I'll showcase the a higher for loop just to see if it goes if it gets any straighter. So kind of put this at 1,000 and making sure we don't slow down our computer that much. What I'm going to be do is adding a if statement where if I modulus 50, or I'm sorry, modulus 100 is divisible by 100 essentially is equal to 0, then we want to, that's when we actually want to graph our figure our updated temperatures. I think we should be good. So that'll just be 10 iterations. Yeah, it looks like we already get it pretty straight. Yeah. I'll go ahead and print RT as well, just to see how well, excuse me, it's changing. It's a little hard to see here, but we have our first one. So all at 50. And essentially we kind of reach a consistent slope here in between, about 2.1 changing. And it looks like it doesn't change after about a year. Our 1, 2, 3, 4, our 5th iteration. So that's 500 in our 10,000 or 1,000 we did. So yeah, remember each iteration was 100. So technically we could just tone this down to 500. It'd be the same. But I know in class, it's a little bit different from the parameters we had from here. I think it was actually these two were flipped. And then we jacked up our for loop to like 1500 to see something like this shape a bit more. So you'll notice that it takes a lot more, since obviously there were more discretizations, and at a lower temperature that would take a lot more iterations for it to kind of reach the same slope. But oh yeah, I forgot that we have all those numbers. But I'll go back to what the problem wants to make sure I don't have to redo this. So again, we are reaching that slope pretty fast. So I think it was around 500 is what I said. So yeah, about 5, it reaches that consistent slope. And yeah, that's about it for the graphing. But remember, our R is this thermal conductivity, or I'm sorry, thermal diffusivity times our delta T over delta X squared. And this number is what's governing our function to essentially not explode. So let's go ahead and make this thing explode. I would make it 1 just to see what happens. Yeah, we got oscillations up to 189, 10 to the 189. That's fun. Awesome. Okay. So I believe the problem wants us to try, let's do the lower one to make sure we don't blow up just yet, 495. So yeah, this is pretty usual as what we had, pretty same visuals we get from when I typed in 0.5, but I believe the higher end number we are testing is 0.505, in which case you start to see these oscillations, and those oscillations will have to do with our stability analysis, in which case we'll discover there are some frequency factors K and some constants which are restricted by our boundary conditions, but essentially we are doing a loop of iterations that allows our temperature profile to kind of increase to infinity, and that's kind of what you see these oscillations happening here. Again, just to visualize what we had in class before, should be very similar. I think I don't have an, oh wow, that's funny. So I didn't actually do enough as we did before in class, but I should be able to jack this up. And okay, maybe a bit too much, but I think you get the point. We are oscillating at these higher R values that we kind of don't want to approach, essentially. So I believe that's it for part 3 of the homework. Now let's get into part 4 here. Switching to, I'm still sharing my screen, and then I'll switch over like so. Awesome. Oh, it's a lot of talking. Another water here. Remember our question for part 4. So we're going to be using something called the Neumann stability analysis to basically see why our R values are approaching this, or I'm sorry, why we can't go over this magical R value that is around 0.5. So what that involves is we'll be doing some substitutions, and we'll actually need to find our, oh, what is happening here? Okay. I guess our temperature as a function, so we can express and kind of find the limits of this R value. Remember, I guess I don't think I mentioned this before, but we express this n and j. Remember that our time is simply just the number of time step times our times discretization, and our x component, our position, is simply our j, the number of, I guess, Lego pieces, times our delta x, remember, our infinitely small slices across. So multiplying those two will get us to our desired time and desired position. So eventually, I don't know if I want to substitute them out now, factor them out now, or also show the derivative. I think it'd make more sense for the derivative first. So remember that from our first expression, in part 1, we had our temperature with respect to time, and then our thermal conductivity, as well as our second derivative with respect to position. So what I mentioned before about needing to find our temperature, this will be without the derivative. So this will be kind of a, kind of slightly more complicated expression than we're used to. But essentially, we want to find a temperature that satisfies, these conditions that we're setting right here. So I'm going to introduce a concept might be familiar with, is Euler's number, or Euler's law, however you want to say it. So it was e to the ix, with I, remember, being imaginary numbers. I is square root -1. So e to the ix, remember, is cosine x plus I sine x. And this will be important later on when we're doing the stability analysis. But keep in mind for now, we can express Euler's number as something like e to the ix minus, or I'm sorry, plus e to the negative ix. So what I'm doing is essentially copying down the first expression that we wrote before, and we're adding on this second expression of negative ix. So adding on cosine of negative x, we know since cosine is a even function, well, that's just the same thing as cosine x. And then we have a plus I sine negative x, while sine is a odd function, meaning this must be a negative I sine x. So you'll see here that we have a sort of addition and subtraction we can do with like terms. Well, cosine, that's just equal to 2 cosine x. And our I sine x's, well, these simply cancel out, plus and minus. So we have 2 cosine x, and I forgot to do a divided by 2 here, but if you divide by 2, we can reduce our Euler's law into just a cosine x. Just some, I guess, helpful know-how in the future, which we'll be needing later. And also, if I put in something like a e to the k, or I'm sorry, e to the ikx, remember that this would just be cosine kx plus I sine kx, with k being any real number. And that'll be important later on as we show that our temperature, just T, is equal to a sort of infinite summation of any number of k, or I'm sorry, any an infinite excuse me an infinitely number options, I guess, for k and c are coefficients, but more on that later. So in my attempt to kind of show and kind of make sense of this so we're not just memorizing, we need to show that our temperature with respect to time nets us this to the right hand side. It's kind of self-explanatory, but we also need to know how to get this second derivative. So if we kind of assume something like our temperature has this ikx formula here, well, let's take with respect to x our first derivative. We have our first derivative with respect to position. This must be, well, exponent rule. Black, can't see that. So we bring down the constants, ik e to the ikx. Second derivative, very similar. We're going to square that number, or that value. And what that actually is, remember that I is square root negative 1. So if we square this, it's simply negative 1. So we'll have negative 1 k squared e to the ikx. So this is some value that must show up on the right-hand side, meaning that our first derivative with respect to time has to include this value somehow. It also means that since alpha did not show up in our second derivative with respect to position, it must also be in our first derivative with respect to time. So kind of rewriting this out here, first derivative with respect to time, alpha, and we have to include somehow the second derivative. So it is negative k squared, k squared e to the ikx. So we have to somehow include this term, and you'll notice that in our first derivative here, there's no negative sign. So obviously this negative sign has to be canceled out by our, I guess, magical second exponential we'll have here. So we know it has to include these two values as well as a negative sign to cancel out this other negative sign. So if I suppose something like our first derivative, or I'm sorry, our temperature is equal to our e to the ikx as before, multiplied by another exponential, And combining everything I said before, well, we need a negative number or negative sign to cancel out this other negative sign. As you know from our original expression, there is no negatives there. And then we also have to have an alpha, as our second derivative with respect to position did not have an alpha term. So we're adding an alpha. And also we need to have a k squared, as no k squared appears in our original expression. So k squared. And we add our time so that we can take that partial derivative. Well, now if we take the partial derivative, we'll be looking at this term. So again, bring the constants out. We have this is equal to negative alpha k squared e to the negative alpha k squared t times e to the ikx. And if you'll notice what we have of our, well, that's a lot of colors. For our second derivative here, you'll notice that it actually already exists right here. I'm sorry, we should also, I guess I didn't include it before, but we need to, after we actually found our missing derivative here, it'll also obviously be a constant in our second derivative since, right? Since again, you're not taking, it's a partial derivative, and that component only has a t component, in which case we don't take that derivative, and it remains a constant. So the actual second derivative will look something like that. And now, if you'll notice, you'll see that these terms already appear in our first derivative. So with a simple substitution, all the terms I circled here drop down to alpha and second derivative dx squared. Hopefully that makes a little bit more sense. Not just something, we memorize that our temperature magically became this, but this will be important later on as we discover the use for that expression. Well, I guess that now would be a good time to explain that as well. So that expression, it's essentially saying that t is equal to an infinite summation, where I is starting at 0 and can go on to infinity. We have a coefficient, any real number, literally infinite, and we have e to the negative alpha k squared t multiplied by e to the ikx. And you'll notice that for any value k, I guess those should be I. Go. For any value k and c, our coefficient, this will satisfy our temperature profile as any given solutions. But you'll also want to notice that we have a imaginary I there in our second exponent. And you'll wonder why that is the case and why we can accept that as part of our solution. Well, remember what I said earlier about Euler's number. This expression of our e to the ix plus e to the negative ix, there is a sort of, for every I, there is a negative I. I'm sorry, for every k, there's a negative k. That kind of balances out and gets rid of this imaginary term with the sign, as you'll notice. So that is why, that is one constraint we have on our solutions. And also that applies to our coefficients for every c and k. That this must be true, in which case the imaginary numbers are canceling out. And another constraint we have is, well, our boundary conditions. We know our temperature has to be some real number defined by our boundary conditions, which we set, remember, in our Python script. That was simply, it has to be a real number at the start at times equals 0, and at the end of the two bars where it was 40 and 80. So that's just another constraint that's held on this infinite summation of our solutions. So with that being the case, then how will we decide what c and k is? Well, that's another story with, I believe, a Fourier transform, which we'll not really get into. But instead, we're going to be now focusing on our stability analysis. And before my Discord breaks here, kind of going back to remember what we're doing. Well, we're going to solve for why this r is set larger than with the r being set larger than 0.5 results in those oscillations. So now we'll finally get into why this is very important, the substitution of time with our discretizations and our number of steps taken, whether it was time or position. So I think what we're going to want to do is take our temperature here, and where are we? So take our temperature, I guess I'll rewrite it. I believe it is e to the negative alpha k squared t times e to the ikx. And we are remember that our t is, go here to the side, simply n number of time steps with our discretization, delta t. X is the same exact thing, except we use j to denote it, and the delta x. So we're literally going to substitute those in for t and x here. So now we're going to define them as t at n and j. I think I did that in the correct order. So e negative alpha k squared, and again t is n delta t, and e for the second term for our position I k j delta x. Now we can use this to substitute in our main formula wherever it is right here. So you'll notice we have the n plus 1s and j plus 1s, so don't let those confuse you. I guess now is a good time to bring that up. So let's start with tn plus 1. So tn plus 1 at the same j. Remember that we still have this component, but we'll treat it like a constant for now. So bring that over here, multiplied by e. And now all I'm doing is substituting the n with n plus 1, so you can see why this makes sense. I'll go ahead and move the delta t over, then n plus 1. So what does this mean? Well, if we break this down further, we can see that it is e negative alpha k squared t delta t. Then we have n. So I guess keep it in our notation we've seen before, n delta t. And remember what the adding exponents means. Well, we have xa plus xb as just, I'm sorry, times xb. I'll go ahead and make them lowercase. That means you're just adding them, a plus b. Literally x1, x1, x squared. Something we've seen time and time again. So adding exponents, well, we factored out a t. So all we want to do is remove this n since it is missing from this second term up here. So since it's missing an n, we just copy down everything else. So multiply exact same constants. Now there is no n, but there is a t. So recall factoring. We're just looking at the common terms here, and the common terms are, as we see, negative alpha k squared delta t. And if we factors those out, just looking at the circled in red, well, negative alpha k squared and then delta t. And what we're left with, well, n and then plus itself, so n plus 1. So that is why we see this extra component of n plus 1, just 1 over here, essentially. So what this means, well, I can say that this is tn, this is 1, so this must be tn plus 1. So hopefully that makes sense. So when I write tn plus 1, essentially all I'm saying is that we have tn plus 1j is equal to the normal tnj. So remember that this is our normal tnj. Well, what's different from this expression and the expression where we had n plus 1? Well, we are missing this extra t1 component. So that's all I'm going to add. Remember that t1 is just e negative alpha k squared without the n here. So just delta t. Same exact thing for j. Should I go through it? I'll just write the shorthand form. Hopefully this makes sense. So let's go t the n for the current position j plus 1. So again, this is just tnj. And then we have our additional j component, which is factoring out a j. Well, what is that? It was e to the ikx. That's it. Remember, I'll just go ahead and do it. Remember that we used to have a eikj delta x. So if we do a j plus 1, it's simply we're adding that extra component that we break down. So this is, I guess, tj plus 1. So again, fairly straightforward. And then you can guess that we don't have a j since we factored it out. So this is just x. And remember how we got the j plus 1 is we found our common factors, ik and delta x. So that we wrote it like so. Exact same thing. Okay. That might have been overkill, but I know this helped me a lot when I was trying to figure out what was happening. So hopefully that explains more. And now we're going to be using those, I guess, expressions that we derived, or I guess broke down into our equation, wherever it went. I'll just write it out again. So we had t t at the next time period at the same time was equal to, or I'm sorry, I did that backwards. Or no, that's correct. And then, so t at the current position at the next time interval is equal to t, or temperature, at the current time at the same position, and that was plus r times our second derivative, which was t n plus 1, or I'm sorry, just n, backwards differencing, so j plus 1 minus 2t j n plus 2 e j. No, not 2. Just tj, and so minus 1, that's what. So at the previous temperature at the current time. So what we're going to be doing is simplifying all of this. I'll go ahead and keep the left-hand side the same, so it kind of makes more sense later on. So we have t and j still the same. This is our baseline plus r. Well, what is t n j plus 1? Remember, we said that was our base plus, or I'm sorry, multiplied by our extra x position component, which was ikx delta x minus 2 of the same exact thing, plus our, so now this is a minus, so we're going to be dividing by a j minus 1. If you remember what minus means with exponents, so we have our base. So instead of adding this extra position, we're going to be subtracting it at the top, which essentially means we're dividing. So now we have our broken down terms here. We can actually factor out our tj here. Yeah, let's not skip steps. So kind of copying everything down here. Factor this out. And I'm going to group together the left and right hand term for the exponents, since you recall that's something familiar we've seen before. This is actually the Euler's expression that we had before. Instead of ikx, well, we had ik and x, now that we have a delta x, but essentially we're treating that the same. So this is plus e to the negative ikx, and then minus 2. So that's this middle term here. So I'll go ahead and do a short breakdown here, and then I'll factor more. So remember, if we go all the way back up here, right here. So remember, this is ix to negative ix, and it broke down to essentially cosine x after we divided by 2. So we're not dividing by 2, so we'll have 2 cosine x. But with the ikx, remember, that's just going in between our parentheses for our trig functions, and we're just left with cosine kx now. And so that is cosine 2 cosine kx. I'll just do it as x and minus 2. Well, this is after factoring all this out. I'll do something like this. We have the j n plus 1, and then factoring out our base t and j, we have our original 1 plus r times r parentheses right here. So actually I can factor out the 2 now as well, so I'll go ahead and do 2r, and that is cosine kx minus 1. So that's enough parentheses. Now you'll notice we have a component here. I'll just call it y. I'll remove all these for now, just so it doesn't get confusing. So we have some function y here that essentially, if this function is greater than 1, well, you'll see why those oscillations that explode our function in Python going to infinity occur. Well, if it's greater than 1, essentially you're multiplying by an iterating factor, where if we add in our previous component, it has to be, I guess this would make more sense if it was like, I don't know, a prime, but that kind of looks like a derivative. So I guess just keep in mind that as we go from the next iteration beyond, that next iteration is dependent on the previous iteration times some factor y. So that factor y, if that factor y is greater than 1, well, our next iterations will be something like tj at n, and then the next one will be greater, since if y is greater than 1, well, it's going to be increasing in size as we continue to iterate. And that is past a certain point, and remember that is governed by some value r. So how do we find that r now that we have this last expression here? Well, we want to assume that the absolute value of our y function, if this is y, cannot be greater than or equal to 1. So we'll say absolute value cosine kx minus 1 cannot be greater than equal to 1. So removing the absolute value, doing some algebra, we do a limit, I guess equality, copy this down. 1, and then we subtract our minus 1 here. So minus 1 would be negative 2. And then again, copying down once more. Kind of see where we're going with this. Subtract 1, this is 0. And dividing by 2, we have negative 1 r cosine kx minus 1. So what does that leave us with? Well, this 0 limit here, that should not be a problem, because if you remember what r is equal to alpha delta t delta x squared. Well, all of these are positive numbers, and it's generally not going to affect this greater than or equal to 0, as well as, since it's being multiplied by this cosine kx function, well, that is a function we know that oscillates between -1 as a minimum and 1 as a maximum. So if we assume the worst possible case scenario at 1, well, 1 minus 1 is equal to 0. So that is generally not a problem for the right-hand side. Well, remember that we also have this left-hand side here. Again, r is what we're solving for. So if we simplify our cosine kx as the worst possible scenario, remember that is -1. Well, -1 minus 1, that is -2. So if we come down and simplify even further, we have r times -2, 0. Remember, right-hand side's not really a problem here, so we'll focus right here. Now we're going to be dividing by a negative number, so we flip the signs, and now we have 1/2 is greater than or equal to r. That is why, with the von Neumann stability analysis, that's what we did here essentially. That is why our r value cannot become, essentially exceed this magical r number. As if we exceed this, that's when the oscillations occur with this kx function. Remember that k we are choosing as a part of infinite sum of coefficients and k's. From whenever I did that, I actually don't remember. Did I even do it? I hope I did. Can't find it here, but wherever it is, remember that's what we were showing it as, did I really not do it? Okay, well, anyway, pretty sure I did it. So hopefully go back. Oh, right here. So we're choosing any C and K's that fulfill our boundary conditions. So that's why that's one condition or restriction for that for those values of C's and K's. Again, for any value of K, we had a negative K that got rid of our imaginary numbers. Remember, our sine x's with our Euler expressions got canceled. And the same could be said for sine, where it was e to the ix minus e to the negative ix divided by 2I, in which case you had a sine of x instead of cosine x. So you would see that the cosines would cancel, and the I times sine x would add up to 2. So that's why we divide by 2I to get rid of that imaginary number. So hopefully that explains everything. You might ask, why we're limited by this R, or if we're limited by it at all. The answer is no. There's something called Crank-Nicholson, which introduces the idea of an average between our expressions of our second derivative. So simply we do a tn plus 1 at these same positions here, and then we subtract that from our original second derivative, what I just circled, and essentially we divide by 2 in our R term, and that's just an average, but that makes solving the math for this expression a lot harder, because we are now dealing with simultaneous expressions or equations, in which case ours is just linear. But if you remember something called Radu, which does nonlinear forward differencing, this is kind of a tangent I'm going on now, but that is much harder than what we're doing right now. And essentially that forward differencing and backward differencing, those ideas come into play here. And yeah, with Crank and Nicholson, we'll be able to show, I believe in class we actually did a von Neumann stability analysis. I'm refraining from doing it now since I have a feeling that might be assigned and I don't want to do it again. But essentially we're doing the same thing of what we just did, subbing in our n's and k's, n plus 1, j plus 1, all those things, so we can get an expression that leads to an inequality like so. Now, I don't remember if I hope I'm right when I say this, but you can double check me on this, but I believe for Crank-Nicholson, the expression was something like 1 minus y, 1 plus y, where y was some funny looking number, but y was always greater than 0. In which case, this function for any r value would not blow up, as since y was greater than 0, a positive number, we would not. It would always be less than 1. Is what that von Neumann instability analysis for Crank and Nicholson would have showed you. So may or may not see that in the next video, who knows, but I believe that's all I wanted to say. So let's just go over the very end, make sure we did everything. So again, we did our time dependent heat diffusion as well as position dependent, and then we substituted our excuse me, our discretizations of t and x, and then we use those to plot our model, our temperature of our uniform bar, the temperature profile in Python, and we discovered that the R values were sort of dictating the stability of that function. And if we exceed a certain R value, which we found to be proven was 0.5 from the von Neumann stability analysis, that is why we could not exceed that number because of the oscillations that would occur, and that would break this inequality that would result in our function iterating to essentially infinity. So yeah, that's all that. Thanks for watching.